This is a short video about the comparison test for convergence of series or infinite sums. And it is short because everything I want to say about comparison tests for series can be summarized by this one sentence. Comparison test for series and comparison test for improper integrals work exactly the same way. In various previous videos, I introduced the comparison test for improper integrals slowly. I explained the statement of the theorems and the proofs and why they work, and some examples of the calculations we normally do with them. I will add a link in the description of this video to the videos where I did all that for improper integrals. Well, everything works exactly the same way for series, so I guess I could end it here. But yes, a quick summary of what these theorems say. First, the main result that these theorems are based on is the following. If I have a positive series, it may only be convergent or divergent to infinity. Other types of divergence are not possible. And as a consequence, if I want to prove that a positive series is convergent, all I have to do is prove that it is not infinity. This is at the basis of all comparison. This is what allows us to write comparison tests. So here is the statement of the two theorems. First, the basic comparison test. For this test, I begin with two series, the sum of an and the sum of bn, and I assume that one is bounded by the other. I assume that the b's are greater than or equal than the a's, which are greater than or equal to 0. I'm saying for every natural number, but as we know, it could be enough if this was true eventually, if this is only true for large values of n. Because for the purpose of convergence, only what happens to the tail of the series matters. So I assume that b bounds the a. And then, if the sum of the a's, the smaller series, is divergent to infinity, then the sum of the b's, the bigger series, must also be divergent. On the other hand, if the sum of the b's, the bigger series, is convergent, is a number, then the sum of the a's must also be convergent, also a number. As you see, it's exactly the same theorem as for improper integrals. Here is the second theorem, the limit comparison test for series. In this case, I begin again with two positive series, the sum of an, the sum of bn, but instead of trying to bound one with the other, I compute the limit of the quotient of the general terms. So I calculate the limit as n goes to infinity of an over bn, and I need to assume this limit exists, is a number, and this number is positive. In that case, the conclusion is that the two series must either be both convergent or both divergent. That's it, again, it's the same theorem. For a proof, I invite you to rewatch the proof of the limit comparison test for improper integrals and convince yourself that you could take the very same proof, replace every integral with a series, and it would work exactly the same way. As for examples of how to use the two theorems, again, I invite you to rewatch the examples I explain for improper integrals and convince yourself that every example would have worked equally well if we had been talking about series rather than improper integrals.